So we are moving on to kind of the last part of this unit, and that is reaction mechanism. So if you remember back, I told you there's two ways to determine a rate law. First is by having data and actually figuring out, well, if this doubles, what happens to the rate? And the second is if you know the reaction mechanism. So we're going to get more into reaction mechanisms now. So reaction mechanisms are essentially a sequence of events that get you from your reactants to your products. Okay, now it could be one step, very unusually, but it could be one step, maybe one or several steps. Most of ours are going to be like 2 or 3 steps. So you got an analogy over here, right? If you're going to do origami, there's multiple steps to get from a piece of paper to an origami penguin. You can try this one if you want to. I haven't tried it yet. But essentially, all these steps in between are what are called elementary reaction steps or elementary steps. So one step by one step by one step gets you from the beginning to the end. And chemical reactions are exactly the same way. So an elementary step is an individual step in the overall reaction. Okay. Again, most reactions, or most of the ones that we're going to look at, have 2 to 3 elementary steps. Okay, so what happens in these steps? There's something called molecularity, and that's like how many molecules have to collide in order for something to happen. So let's write that down first. Number of molecules with, again, the correct orientation and enough energy to collide for an elementary step. Okay, so it could just be one thing having to collide with one thing. It could be 3 different molecules having to collide at the same time. It could be 4 or more. Usually they are going to be unimolecular or bimolecular reactions. Okay, most common. And if you think about it, that's because things like termolecular, meaning they have to have 3 things that collide exactly at the right place at exactly the right time, are very unlikely to happen, right? If you're thinking about collision theory, they have to be in the right orientation and have enough energy. So the more molecules you're bringing in to actually make that collision, the more difficult it's going to be. Okay, so most of the time we're going to see these guys down here are very rare because they're so specific. All right, to get a successful collision is very difficult. So most of the time we see uni and bimolecular reactions. So why do we care? Why does this matter? What's going on with the mechanisms? Well, since there's 3 different steps or 2 different steps in a lot of reactions, the rate is actually affected by that. So one thing I like to say is essentially you're only as good as your worst step, or you're only as fast as your slowest step. So for example, if you're running a relay, you can only go as fast as your slowest person, and you can't go any faster than your slowest person. Or if, that's another example. I say this with SigFix, you're only as good as your worst measurement. Okay, so if I have 3 funnels and I set them up in different ways here, the little one is going to fill the fastest no matter what. It's going to go straight through these big ones. This is actually my rate determining step in these 3 steps, because it can only go as fast as the small funnel can fill. All right, so one step is always slower. There's always one that's slower. One step is always slower, and that's the one that affects the overall rate. Right, if you look at these examples over here, if I make the bigger ones bigger, it's not going to make any difference in my rate. However, if I make my little one bigger, then that would actually speed up the process of getting through. All right, so you're only as fast as the slowest step. Okay, so the slow step is always called the rate determining step. Okay, so as we're doing these reactions, this is another vocabulary word you're going to need to know, and that is, what is a reaction intermediate? So if I've got multiple steps, sometimes I'm making a product that's going to get used in another reaction. That actually happens a lot. So the reaction intermediate is a molecule that is produced in one step and then consumed, or it's a reactant, in another. Okay, so it gets made and then it gets used up. All right. So it's actually something that cancels out and isn't present in the overall reaction. So what do I mean by that? If you think back to Chem 161, Hess's law, when you have like multi-step reactions and you add them all up to get your overall reaction, that's what we're going to be doing here for our mechanisms. Okay, so reaction intermediate is something that is made and then consumed. So we got a couple examples here. I have an overall reaction here. NO2 plus CO makes NO and CO2. So the rate law is experimentally found to be this. Remember, we can only find rate laws by experiment or if I know the mechanism. So I'm giving a proposed mechanism. So anytime I ask, is this a potential mechanism for this reaction? There are two things that you have to check. First of all, do the steps add up to the overall reaction? All right, so we're going to check that first. All right, we're going to write our overall reaction. Now, if you have something on the product side and the reactant side, it is going to cancel out. So for example, NO3 is a product in the first step and a reactant in the second step. So that one's going to cancel out. Okay. Also, there's an NO2 on the right side, so that's going to cancel out one of the NO2s on the left side. So what I am left with here is NO2 plus CO makes NO plus CO2. And yes, there you go. That does match my overall reaction. Okay, so yes, one, it does add up. Now, second, does the slow step match the rate law? Okay, because remember, the rate is only as good as your slowest step. So I said the first step is slow. So what I mean by this, what you're going to check is actually the collisions that happen in the slow step are what affect the rate law. So for example, if I have two NO2s colliding in my first step, that means that my rate is based on the NO2 concentration, two of them. So that would mean NO2 squared. So this does work. But essentially what I want to write is the collisions in the slow step equal the rate law. Okay. So if I look at this, my slow step is my first step. And in order for the first step to happen, I have an NO2 colliding with an NO2. So I need two NO2s, and my rate law is NO2 squared. So yes, this one does work out. Okay, so essentially the rate law, those powers, those orders have to match the slow step. Okay, so we're going to do another example here. This is nitric oxide and bromine making NOBr. And I gave you, again, experimental rate law and a proposed mechanism. So if I want to know if this is correct, remember, you're going to have to check those two things. First of all, I gave you rate constants for this one. It says rate constants are labeled as K1, K-1, and K2. So the next chapter is really about equilibrium and reactions that are reversible. They can go forward or backward. So this might make a little bit more sense after I do the next lecture as well. But equilibrium just means that it can go back and forth. Okay, so at equilibrium, it kind of steadies out. But I'm giving you Ks for each of these, and there's a reason for that. We can just call them whatever, right? So K1 goes with the forward reaction, K-1 would be the backward reaction, and this one is K2. All right, so each step has its own K value. All right, so is there a reaction intermediate, first of all? Remember I said a reaction intermediate is something that is produced in one step and then used in another. Well, yeah, I've got NOBr2 is produced here and used up over here. So yes, NOBr2 excuse me, is a reaction intermediate. Now, the second part says, is this a possible mechanism for the reaction? So there's two things we have to check. Remember, do they add up correctly? And does the rate law match the slow step? So let's add these guys up here, make sure that they add up to the overall reaction I want. NOBr2 is going to cancel out. So I will have two NOs plus Br2 makes 2 NOBr. So yes, so I checked my first thing. One, overall reaction, check, is good. Second thing I need to check is the slow step. Does it match the rate law? Okay, so I'm looking at my rate law here, and if I were to write a rate law for the slow step, I would write rate equals K times NOBr2 times NO. Now this is super weird because rate laws can only have reactants from the overall mechanism in it. So if your slow step is the second step, you're actually going to have to do some substitution. So I'm going to show you what that means here. Okay, so if your slow step is the second step, okay, when slow step is second, we're going to have to do some substitution. Okay, and what I mean by that is we're also going to have to write the rate law. We need to get rid of NOBR2, essentially. That can't be in my rate law because it's not in the overall reaction. It's not a reactant. So I have to see what NOBR2 is actually based on. Okay, so what I'm going to do is I'm also going to write a rate law for the first step here. So rate of the first step should be K times NO times BR2. Okay, so rate of my forward reaction is K1 times NO times BR2. Now, at equilibrium, the forward and the reverse reaction, because this is an equilibrium one, this is another thing we're introducing here, the rates of the forward and the reverse are the same. So I'm writing the rate of the forward is that. The rate of the reverse would be K -1 times the reactants in the reverse equation would be NOBR2. I'm looking up here, I pulled that from this. So what I did is I wrote a rate law for the first step, okay, the forward and the reverse reaction, because it can go both ways. So these are actually equal at equilibrium. So I'm going to set these equal to each other, K -1 times NOBR2. So again, why am I doing this? This guy here cannot be in my overall rate law because he's not a reactant. So I want to substitute him out. So I've got this equation here. So I'm actually going to rearrange it so that I get just what NOBR2 equals. So that would equal K1 over K -1 times NO times BR2. So now I can actually substitute this in here, and then that will give me the actual overall rate law. Okay, so now what I've got is my rate equals, okay, that one was K2 because that's from the second reaction, times I'm substituting in here, K1 over K -1 times NO times BR2 times NO. Okay, and then you can simplify rate equals, now K is a constant. We're not trying to calculate it right now. So I'm just going to combine all those K's and just, it's a new constant, okay, times NO, whoops, squared, there's two of those, times BR2. Okay, so that should be my rate law if this is the correct mechanism. And oh, would you look at that? That's what I said the rate law was. So yes, the slow step does match. Okay, so anytime you do one of these, you're going to have to use that substitution when the slow step is the second step, okay? All right, on to reaction diagrams for multi-step reactions. We kind of already talked about reaction diagrams, but they do look a little different. They've got two humps if it's got two steps, okay? So there's a hump for each step, essentially. Okay, each step has its own activation energy. Each step has its own EA. Okay, the valley is where the intermediate is. Intermediate, because it's kind of like a stable intermediate reactant that is then going to get used. Okay, you can determine which one is the slowest step by also looking at this. Can determine the slow step, aka the rate determining step. It's the one that has the the highest activation energy. So by highest EA. Okay, so essentially what that means is the most difficult step, the one that takes the most energy, is going to be your slowest step. Okay, so in this case, step 1 has a higher activation energy, so it's more difficult for it to get going. So step 1 in this case is the slow step. That's it.